Here we're going to work through some review problems for preparation for the chapter 3.1 to 3.5 test. So here we see f of x is equal to x cubed minus 12x, and we want to find the intervals for which f is increasing, decreasing, concave up, concave down. So the increasing, decreasing questions are questions that come from the derivative. So we'll find f prime of x, and that's going to be 3x squared minus 12. We want to know where is that equal to 0. So if we factor out the 3, then we'll get x squared minus 4, and that factors further into x minus 2x plus 2. And so we can see that when x is 2 or negative 2, the derivative will be 0. So we can look now at our number line. We'll label it the f prime number line. We can see that this will equal 0 at negative 2 and 2, and we're looking for what's the sign in each of those intervals. So if we plug in a representative from the left side, say negative 3, then 3 is always positive, negative 3 minus 2 is negative, negative 3 plus 2 is negative, and the product of a positive, negative is positive, so it's going to be positive to the left of negative 2. Take a representative for the middle interval, say 0. So when we plug that in, we'll get 0, 0 minus 2, I think that's still going to be negative, but 0 plus 2 is positive. The product of a positive is negative. And to the right of 2, we'll plug in, say, 3, and everything becomes positive. And so we can see the signs of the derivative. So from the sign of the derivative, we can tell where f is increasing. So f will be increasing on the interval for x less than or equal to negative 2, and also for x greater than or equal to positive 2. And f will be decreasing then on the interval from negative 2 to positive 2, and we'll include the endpoints on increasing, decreasing, as long as the function is defined there. To talk about the concavity, we need the second derivative. So taking the derivative of the derivative, we'll get 6x. We'll see where is this equal to 0, and that will be at 0. We'll do a number line then for the second derivative, and at 0, this will be 0. If we plug in a negative number, something to the left, then 6 times a negative is negative, and in a positive, we'll get a positive. So where the function will be concave up when the second derivative is positive, so that will be on the interval for x strictly greater than 0. And it'll be concave down where the second derivative is negative, and that's going to be x strictly less than 0. Notice we don't ever include the endpoints on intervals where a function is concave up or concave down. So looking at the next one, we have f of x is x plus 2 squared of x plus 3 all over squared of x, and we're trying to find f prime of x. So we could use the quotient rule. I would not recommend that. I would say let's first, before we do any calculus, let's split this up. Since we have a monomial denominator, just a single term, we can split this up, do some algebra and simplify things, and then take the derivative after that. So using our properties of exponents, this is x to the first over x to the 1/2. That's going to be x to the 1/2. The square root of x's will cancel in the second term, and 3 over square root of x is the same thing as 3x to the negative 1/2. Now it's in a more derivative-friendly form. So the derivative, we can get 1/2 x to the negative 1/2. The derivative of 2 is 0, and then a negative 3/2 x to the negative 3/2 power. This would be fine. You can leave it like that. If you feel like flaunting your knowledge of these exponents, I'm going to put or here. So, or you could write that as 1 over 2 square root of x minus 3 over 2, and then call that the square root of x cubed. So that's an alternative version of that derivative. Let's go to the next panel here. So now we have y equals 4x to the third cosine x. And remember, this is our Leibniz notation for the first derivative. So to find dy dx, we're going to use our product rule. So we have the first, 4x to the third, times the derivative of the second, which is a negative sine x, plus the second, cosine x, times the derivative of the first, which is going to be 12x squared. So we'll do a little cleanup here and bring the negative from the negative sine x out in front. So that's a negative 4x to the third sine x. And then we'll bring the 12x squared to the front. So that's 12x squared cosine x. So there is our first derivative. And so then we will find our second derivative. So the second derivative of y with respect to x twice, we're going to have to use the product rule twice here. So we'll get our first, negative 4x to the third, times the derivative of the second, which is going to be a cosine of x, plus the second, sine of x, times the derivative of the first, which will be a negative 12x to the second. Then, product rule for that second term, we have the first, 12x squared, times the derivative of the second, that's a negative sine x, plus the second, the cosine of x, times the derivative of the first, which is 24x. So let's see what kind of cleanup we can do. Let's see, it looks like a negative 4x to the third cosine x. We can make that a minus 12x squared sine of x, a minus 12x squared sine of x, and a plus 24x cosine of x. We see that we have a couple of these that are like terms, so we should combine those. So that is going to become a negative 4x cubed cosine x minus 24x squared sine x, and then a plus 24x cosine x. And that's going to be our second derivative right there. Okay, on to the next one. Here we have g of x is tangent x over 1 plus sine x. So to find g prime of x, we're going to need to use our quotient rule. So we are going to take our denominator, 1 plus sine x, times the derivative of the numerator, and the derivative of tangent x is secant squared x, minus the numerator, tangent x, times the derivative of the denominator, which is going to just be a cosine of x, all over the denominator, 1 plus sine of x squared. So we should look for things we can clean up. I guess we can distribute here, and we can get secant squared x plus, and remembering that secant is 1 over cosine, so multiplying by sine is not going to give us any kind of cancellation. So I'm just going to write the squared term first, but that doesn't make any difference at all there. That's secant squared sine x. Now, when we do the next one, we should remember that tangent x is sine x over cosine x. So when we multiply that by cosine x, we need to see and recognize that those cosines are going to cancel, and so we'll get just a minus sine x. And then there's not really anything we can or really want to do with that denominator, and so that is going to be our final answer for the derivative. Let's see what the next panel is in store for us. Looks like we're going to find an equation of a normal line to y equals x e to the x at x equals 1. So a normal line is perpendicular to the tangent line. So to find an equation of a line, we need a point and we need the slope. So we have an x-coordinate of 1. If we plug it into our function, 1 times e to the first is going to be just e. So our point is going to be 1 comma e. To find the slope, we have to first find the derivative. And so that's going to be a product rule. We have the first times the derivative of the second plus the second times the derivative of the first. We want to evaluate that at x equals 1. So that's going to become 1e to the first plus e to the first is going to be 2e. Now that's the slope of the tangent line. Remember, the normal line is going to be perpendicular to that, so it's going to be the negative reciprocal of that slope of the tangent line. So the slope of our normal line is going to be 1 over a negative 1 over 2e. So in point slope form, this is going to look like 1y minus e is equal to negative 1 over 2e times x minus 1. Kind of goofy, but there's our tangent line. So now we want to find y triple prime, the third derivative. So this is really just trying to make us, I'll use the prime notation, make us understand how we differentiate a to the x. So remember, that's going to be 2 to the x times natural log 2, and then we'll get a 7 to the x times a natural log 7. So there's our first derivative. Our second derivative, now remember this natural log 2 is just a constant, so the derivative of a constant times a function is just the constant times the derivative of that function. So we're going to get from the 2 to the x another 2 to the x natural log 2, which is going to get multiplied by that natural log 2 that was already there. So that's going to be 2 to the x, and we can write natural log of 2 squared as putting the square over the n, kind of like we do with sine and cosine. Continuing, we get the derivative of 7 to the x is 7 to the x natural log 7 times that constant natural log 7 is going to make this 7 to the x times the natural log squared of 7. Now we're ready for the third derivative, and as you may be seeing here, we're going to get 2 to the x times natural log 2 times that natural log of 2 squared that was already there. We're going to get a 7 to the x natural log 7 times the natural log of 7 that was already squared. So combining those natural log of 2's and natural log of 7's, we're going to get, strangely enough, 2 to the x natural log of 2 cubed plus 7 to the x times the natural log of 7 cubed, or natural log cubed of 7. All right, very good. We'll leave it there.